For the synchronous motors, different torques and problems. Here, the objectives are different torques of a synchronous motor and problems and problems. Here, the torques are different types. The first one is starting torque, and the second one is the running torque. Starting torque is the torque developed by the motor when rated voltage at rated frequency is applied to its stator winding. It is also called as starting torque. Once again, I am repeating. It is the torque developed by the motor when rated voltage at rated frequency is applied to its stator winding. So very important. So when rated voltage at rated frequency is applied to its stator winding. So this is called as starting torque. Now running torque, it is the torque developed by the motor under normal running condition. So it is torque developed by the motor under normal running conditions. It is determined by the power rating and speed of the drive machine. Power rating and speed of the driven machine. So now next one is pull-in torque. So pull-in torque means here it is the torque at which the motor will pull into step into synchronism when changing from synchronous mode of motor operation. It is the torque at which the motor will pull into step into synchronism when changing from synchronous mode of motor operation. Pull out torque, it is the maximum torque which a synchronous motor can develop without pulling out of step. Once again, pull out torque is the maximum torque which synchronous motor can develop without pulling out of step. That is called pull out torque. Now problem here, the synchronous reactance for phase of a three-phase star connected 6600 volts. Synchronous motor is 10 ohms for a certain load. The input is 900 kilowatts and the induced line EMF is 8900 volts. Calculate the line current. Solution is three-phase star connected synchronous motor. Supply voltage is 6600 volts. And here this is the star connected. So voltage is given line. So we'll convert into phase voltage. So here phase voltage is equal to line voltage by root 3. We will get the 3810.5 volts. Now induced EMF equal to 8900 volts. This is the induced EMF voltage, and induced EMF for phase is 8900 by root 3, which gives the 5138.42 volts. Now input power, that is equal to 900 kilowatts Synchronous reactance Xs is 10 ohms for phase. Now input power for phase is 900 by 3, that is 300 kilowatts. Now Zs is equal to Xs, that is 10 ohms per phase. The armature resistance is neglected here, and power is equal to, what is that maximum power formula, is equal to V into EB by Xs and sin alpha. Sin alpha, alpha is the load angle. Now E R is equal to V square plus EB square minus 2VB cos alpha. So that is, so here substituting this power and voltage and EB and the axis value, will get the sin alpha. Sin alpha is 0.1532 and load angle is alpha is 8.81 degrees. Now resultant EMF, that is ER, is equal to under root of V square plus EB square minus 2V EB cos alpha. Here is the formula for resultant EMF for phase. Now here ER is equal to under root of V square plus EB square minus 2V EB cos alpha. So from that equation, by substituting V EB and cos alpha, we'll get the value is ER. How much the value is? 1491.44 volts. That is the voltage. That is the voltage, resultant voltage. Now the armature current for phase IA is equal to ER by ZS, that is equal to 1491.77 by 10. It is nothing but 149.12 amps. For star connection, IL is equal to I phase is equal to IA, that is equal to 149.12 amps. So now problem 2. So once I can read it. Read once again. See here. A 6600 watts star connected 3-phase synchronous motor works at constant voltage and constant excitation. Its synchronous reactance is 0 plus J20 ohm surface when the input is 1000 kilowatts. The power factor is zero point 0.8 leading. Find the power factor when the input is increased to 1500 kilowatts. So this is the problem. What they given here, 6600 volts line voltage and Xs is J20, Input is 1000 kilowatts and the power factor is 0.8 leading. Find the power factor when the input is increased to 1500 kilowatts. That is the question. For three-phase star connected synchronous motor, supply voltage VL is equal to 6600 volts and voltage for phase V is equal to 6600 by root 3, that is 3811 volts. That is the phase voltage of synchronous motor star connected. So now cos pi is equal to 0.8 leading and pi is equal to 36.87 degrees. Now here the synchronous impedance, the phasor diagram is given. The voltage along with the x-axis V is taken as a reference and IA is leading with voltage by pi angle with pi angle and ER and I is theta and EB load angle. Here the V and EB will get the result ER. Here synchronous impedance that is equal 0 plus J 20 ohms per phase. Now here they given RA is equal to 0 and ZS that is equal to XS 20 ohms per phase and theta is equal to 90 degrees. Theta is equal to 90 degrees and theta plus phi is equal to 90 degrees plus 36.87, that is equal to 126.87 degrees. 126.87 degrees. Now here the total input power P is equal to 1000 kilowatts, that is nothing but P is equal to root 3 VLIL cos pi. The line current IL is equal to, so here from the power equation you get the line current IL is equal to power by root 3 VL cos pi. Now IL is equal to, so power is 1000 kilowatts divided by root 3 6600 into 0.8. So here 109.35 amps. For star connection IL is equal to IA, that is equal to phase current, that is equal to 109.35 amps. Here impedance drop for phase is ER is equal to under root of V square plus CB square minus 2V EB cos alpha. So here that is by substituting these equations V and EB and alpha under root 3811 square plus 2187 square minus 2 into 3811 into 2187 into cos 126.87 under root. So this we get 5414 watts. This is the value of resultant impedance drop for phase. So now when input is increased to 1500 kilowatts, so constant excitation, The excitation, the back EMF is constant. The input power is 1500 kilowatt and power for phase is P is equal to BEB sin alpha by XS. Now here from that equation, say observe this one, power equation P is equal to VEB sin alpha by XS. So here knows the values of V, V, EB and XS. How can we get the sin alpha? Here sin alpha is equal to P into XS by V into EB. That is the sin alpha formula. So here sin alpha by substituting power BEB and get the sin alpha. So 1500 kilowatts and 3811 V and B is 5414 and sin alpha by 20, that is equal to sin alpha is equal to 0.485 and here the load angle alpha is equal to 29.01 degrees and ER is equal to under root of V square plus AB square minus 2VB cos alpha, that is nothing but under root of 3811 square plus 5414 square minus 2 into 3811 into 5414 cos 29.01. So which gives the value 2783.34 volts and armature current for phase is IA is equal to ER by ZS. So that is equal to 2783.34 by 20, that is equal to 139.17 amps. Now power factor, that is the cosine angle between the voltage and armature current, cos pi is EB sin alpha by IAXS. Here we know the value of EB and sin alpha and IA and XS. So by substituting those, we get the cos pi. Now here cos pi is equal to 5414 into sin 29.01 by 139.17 into 20. Now that is 0.943 degrees leading. This is the power factor of the given question. So now, so we have discussed in this class different torques, that is pull out, pull in and starting torque and running torque, and we did the problems. So this is about the so synchronous motor. Thank you.